Hey guys, so on Monday we did section 11.2, techniques for evaluating limits, and we went through a couple of the techniques. Last week I talked about the idea of one-sided limits when you are looking at your function and you are evaluating a limit as it approaches x from the left or the right. Your book actually brings up one-sided limits in section 2. I wanted to bring it up earlier just because I find that a little bit easier to comprehend and help us to understand what it means to be a limit. So if you need to, take a few seconds and read this and also write down the notation here. So remember, c raised to that negative sign means you are finding the limit as you approach x from the left of c, and then that plus sign would be you are approaching your function, you're looking for the value of your function as x approaches c from the right. So since limits, we're dealing with the notation of your limit, the number that your function's approaching is L. In this, your book uses L1 and L2 to talk about limit from the left and limit from the right. All right, so let's review that. Find the limit as x approaches 0 from the left and the limit as x approaches 0 from the right for this following function right here. Absolute value of 2x over x. On the right hand side graphically, that is the graph of f of x, both of those black lines there with open circles, because when x equals 0, that is a value that makes your denominator equal 0, so your function is undefined there. So the first one here, I'm just going to call this a. The limit as x approaches 0 from the left of this graph. You are looking at this right here. From the left, it is approaching the y value -2. So that limit is -2. Part B, you're looking at as x approaches 0 from the right. So this guy, and your y value as x approaches 0 from the right is +2. So those are your one-sided limits. All right, so hit pause and graph this. You can use a calculator if you'd like, and you are finding the limit of f of x as x approaches 3 from the left and the right. All right, I just drew a rough sketch here. So our limit as x approaches 3 from the left, so that minus sign of, I'm just going to say f of x just for the sake of time. That would be my green section of my graph here. That y value is -1. The limit as x approaches 3 from the right of our function is +1. Right here, the y value. All right. So the existence of a limit. So our limit exists as long as the limit as x approaches c from the left and the right both exist, and they are both equal to the same number, which we are calling L. All right, so we're finding the limit of this piecewise function here. F of x equals these two pieces when x is less than 1 or x is greater than 1. So for the sake of time graphically, on the right hand side, that is the graph of our piecewise function. This here, 4 minus x, is our linear part of our graph here, and we graph it to the left of 1, not including 1, so that's why there's an open circle. And then our quadratic here, when x is greater than 1, so open circle here, and our quadratic, all the values of x greater than 1. If you notice, both pieces of that graph, the open circles are connected. That's nice. So let's just go back and think of one of the techniques that was used in evaluating limits in 11.2 part 1 on Monday. So looking at 4 minus x and 4x minus x squared, we can use direct substitution. 1 isn't a domain restriction for any of them. I know x is not equal to 1 here, but we can still plug them in. So for this one, for the left-hand side, as x approaches 1 from the left, we're actually talking about all of these values, and we're going to use that function. So we're going to use direct substitution and plug in 1. So the limit as x approaches 1 from the left of our function is 3. And then as it approaches 1 from the right, we're using that function, and we can use direct substitution. So 4 minus 1, that is also 3. Since your left-hand limit and your right-hand limit are both equal to 3, we can conclude that the limit as x approaches 1, without any symbol here, we're just talking about the whole entire limit, of our function f of x equals, in fact, 3. All right, probably the most important thing you're learning from me this year as pre-calculus connects to calculus here. We're going to find the limit of this function of our difference quotient, and you're going to learn a lot more about what this difference quotient is. I'll touch briefly on it later in this chapter, but you're going to use this difference quotient a lot in calculus next year. So for our function here, f of x equals x squared minus 1, we're finding our limit of the difference quotient, and the difference quotient is given to us here. So f of 3, you're plugging in 3 into your equation. F of 3 plus h, you're plugging 3 plus h wherever you see x. So our limit as h approaches 0 of that difference quotient, f of 3. Well, f of 3, f of 3 plus h. I'm plugging that in for x. So 3 plus h squared minus 1. That's my first one. I'm going to put it in a box. That's my f of 3 plus h minus f of 3. What is f of 3? Well, 3 squared, 9, minus 1 is 8, all over h. Using algebra, we need to simplify here, so we're foiling. So 9 plus 6h plus h squared minus 1 minus 8 all over h. And we still have this limit as h approaches 0. Simplify as much as you can here. 9 minus 1 minus 8. Those all cancel. So we have the limit as h approaches 0 of 6h plus h squared over h. If we use direct substitution and we plug in 0 for our h's here, we would have 6 times 0 plus 0. So we would have 0 over 0, which is indeterminate form. But that also, as we learned on Monday, if we get this, when we plug in 0 for our numerator and our denominator, that means that they have a common factor. So think, what is a common factor that both the numerator and the denominator have? If you said h, that is correct. So we're actually going to factor our numerator. So limit as h approaches 0 of, factor out an h, 6 plus h over h. Our h's cancel. So now we have the limit as h approaches 0 of 6 plus h. Now use direct substitution again, plug in 0 for h. So 6 plus 0. Our limit, in fact, for this difference quotient is 6. So our limit of our, as h approaches 0, of our difference quotient up here, our answer to this is 6. Alright guys, that's it. That's all I have for today. You are going to be working on the one-sided limits and also finding limits of these difference quotients and practicing them. And we will get back to some other stuff coming up on Monday. Please let me know if you have any questions. Thanks, guys.